Well, looks like just two of us here. Okay. Okay, cool. So, sorry for the change of plan. Um, actually, I think today there is no demo, and so I want to have this class earlier than the plan schedule. So basically today we're going to talk about share coding, which include how to write share code, develop share code, and what other things share code can do, and also how do we make the share code more injectable to make it bypass all kinds of sanitizers. So some of the materials I cover today, they were discussed in many books. Some of the books are a little bit old, but they still work. For example, the Share Coders Handbook, like this one. If you are interested, you probably can get this for like $3-4 on Amazon, because this has been like 10 or 15 years old. And also this buffer overflow attack book covers a lot of interesting attacks beyond the buffer overflow. So first we talk about what is local share-code. Actually, local share-code is the share-code you have been using in this class. In this class, I give you multiple versions of share-code to use. They are like 20 bytes, 30 bytes. What we do with them is we either get a shell. To get a shell, we first need to call setuid. Otherwise, we just open a file and print out the content of the file. So the limitations of those two pieces, maybe 4 pieces of share code, is because we're talking about 32-bit and 64-bit, is you need to have a local access of the computer, local shell first, right? Then you can run this share code. Then this share code can give you the shell or flag. But in some real world attack, or in our case, it will be ethical hacking, you may want to break into a remote system. And obviously, this is a chicken egg problem. If you want to break into a remote system, how can you get a share of that system, then try to hack and get a lot of share, right? That makes sense here. So that's why so far we're doing what we have been doing fall into the category of local share code. So today we will first talk about what is a remote share code and several different types of remote share code. Actually, they are very, very simple. If you are a good C programmer, you will say, oh, this is a really, really simple C programming. The difference is you need to get the instructions of that. You need to get the assembly code of that instead of developing this in C, right? For example, the first remote share code we're talking about is the port binding share code. And the idea of this is there is a remote server an attacker wants to hack, and attacker can only talk to on the remote server. There is already a vulnerable function, and that vulnerable function will take some input, and that input may trigger a buffer overflow, may trigger a format string vulnerability, which we will talk about in the later half of the class, or trigger many other vulnerabilities. So after we trigger the segmentation fault, attacker obviously eventually want to fully control the computer or get the flag, right? But in this case, the attacker doesn't really have a local shell there. So the attacker has to somehow get a shell, create a shell on that server, on the victim server, and make that shell listen to our remote commands like cat flag. It will be a remote command, or it will run cat flag, but send that back to the attacker's computer through internet, right? So this is called the remote shellcode. So on this slide, the left-hand side shows the basic idea of this remote shellcode. Of course, the shellcode is not a C function. It is not a C code. It doesn't have a main function. But the idea is like this. So remember, we have been writing some shellcode, right? We have been writing, open a file, then send the file to a specific file descriptor, right? So that piece of shellcode, there is a piece of C code corresponding to that. But we write assembly code to do the same thing, which is equivalent to the C code and get the instructions. Here is the same idea. You need to write the same equivalent assembly code to this piece of C code and get the instructions. But the C code will be easier for us to understand the logic here, what we're doing here with the shellcode. So let's say, so the function main doesn't really matter here. What matters is inside this function. So at the beginning, let's say we create two integers, and the integers in the Linux system is basically file descriptors, or file descriptors are basically integers. So what we are really doing here is we are creating two file descriptors. So everything in the Linux system can be abstracted as a file, and a file has an ID that's a file descriptor, right? For example, the socket, the network, can be abstracted as a file descriptor. If you open a file from the local storage, that is a file. That is also can be abstracted as a file descriptor. In this case, we can create two file descriptors. One we call it new sock, and we didn't initialize its value. Another one is called sock fd, and this one we initialize its value. We initialize it using the socket function. So this is a socket function, which will also be a system call. And this will create a TCP socket. The parameters we are giving here make sure that we are creating a TCP socket. So after that, the TCP socket has a file descriptor, and that file descriptor is this sock fd. Obviously, that file descriptor can be used for reading and also writing. Then, in the next 4 lines of code, we are basically creating the remote parties. No, there's a local address and local port number. So in this case, we are creating a socket address object. And in this object, we say, oh, this is an internet address. The address here is 0, which in this case indicate this is a local server. We're not really assigning any address to this. The address we're going to use the IP address of this computer. The next line, we specify which port number we want to use. In this case, we want to use port number 12345. So that will be our port number. Okay. Then after that, we bind that file descriptor we created at the beginning with this address. Then after that, we are ready to accept or listen to TCP requests. So we make another system called listen, and we say we are listening on this file descriptor, and there could be a queue for this service. And we have, there can be at most 5 requests in the queue. If there are already 5 requests in the queue, when the 6th request comes, then the program will just decline the request. Then after that, this program is ready to accept TCP requests. Basically, the TCP, the first step of that handshaking. To do that, we call the function accept. So all of those functions, the socket, bind, listen, and accept, they have a corresponding system call. And we already know how to write system calls in assembly, right? So this accept function will create a new connected socket identified with a file descriptor and return that file descriptor. So that's why we created the new sock at the beginning. So if there is an incoming TCP request, then we will create a new socket, and that new socket will have the new sock file descriptor. So who will be collecting to this service? It will only be the attacker, actually, right? So the attacker first exploits the vulnerability in a program on the server. Then we inject this piece of code to turn that existing program into a new program by running this piece of code. So turning that program into a server, basically, right? Then that server, a TCP server, will be listened to the attacker's commands, right? So after that, there is a lot of problem to solve. So the program we're attacking, it may be a terminal program, it may not be, it may be a GUI or whatever. So, however, the input and output and also standard error of that program, or in this case, maybe the most important one is std in and std out. They are probably a mapping to the terminal, same as what we had in all of our examples so far. Right? So the std in, std out, std error, they all point to the terminal. So now we need to change those std in, std out, and std error from the terminal to the socket. So when we do that, the program is not taking input from the terminal anymore. The program is taking input from the socket. And the socket goes through the TCP IP stack, goes through the internet, and eventually talks to the attacker. So that is how we can make this remote. So to do that, we only need to change the first three file descriptors of this program to the socket we just created. And the system call or function to do that is the dupe2, okay, which is the function to and system call to duplicate the first file descriptor to the second file descriptor. So the first file descriptor right now points to our socket. It has a number. Now we duplicate to 0, which is std in. Then we keep duplicated to file descriptor 1, which is std out. We also duplicated to file descriptor 2, which is std error. So after that, all those three file descriptors do not point to the original ones anymore. The original ones may be the terminal. Now they point to the socket. Then after that, we just need to do execve to create a shell. And this execve will not change the file descriptor, which means we are getting a shell. However, this shell will be running on the server, but this shell is not taking input from terminal. This shell is taking input from the socket. Then the remote attacker will only need to connect to that socket and send commands to that socket. Then those commands will be forwarded to the shell to execute. And when the shell returns anything, it will not return to the terminal. Instead, it will return to the socket as well. And by doing that, we get a remote shell. And this is the port binding technique. So do you have any questions? Does it make sense?
No, but are you going to have examples of this?
This is the example. So you're talking about where we have a demo?
Yeah, the application probably.
We don't really have a demo for this. Yeah, at least for now, we don't have a demo for this. Yeah. I think we can try to have a demo, but we need to change some firewall settings, everything. It will take some time. So do you have any Linux system programming experience or socket programming experience?
I haven't used any socket, but I used in Linux before.
Okay. Yeah, so this is basically related to socket programming and also a little bit Linux programming. But this will not be our homework or exam anyway. Yeah, so this week's homework will not be like this. Okay, so this is an example shellcode with similar logic. It's like 120 bytes or something to do this port binding. So the previous approach still has some disadvantages. For example, in the previous example, we reserve a very big number, a big port number, and we are listening at that big port number. Some network firewalls will decline that, like at the router and other places. If there is a unknown TCP request to a big number port, we may just decline that. The firewalls can do that. So to bypass that problem, there is another approach. It's called the socket descriptor reuse approach. It's actually a very similar approach. It's just the idea is we're not going to use a huge port number. Instead, we are going to find an existing port number that is already in use. So we are going to reuse that. So no matter which program is using that port number, we take it over. That's it. So if that program is still using that port number, then maybe we are getting many different messages from different sources. That may be a problem. But for attacker, we just need a very short time period to hack a system. So if we look at this piece of code, we can say that we first have an address, then we get the size of address, then there is a big for loop. The for loop use a system call called get peer name, and this basically returns the address of a connected computer to a socket file descriptor. So the reason we are doing this is we are looking for existing socket descriptors. We are just goes through all the file descriptors, and from the file descriptors, we are trying to say which one is a socket descriptor. After we find the socket descriptor, then we get its port number at this object, and from there we try to use that port number. So then we are going to do the same thing. We duplicate several file descriptors. That we find that the existing file descriptor we duplicate that to std in, std out, and std error. Then we execute the share program. So that is how it works. The third approach is to get a reverse collection shell. So in this case, the share code will make a collection from the exploited system to the attacker's system. So once the share code is collected, it will create an interactive shell, right? So because in this case, the TCP request is initiated from the exploit system instead of from attacker, it's less likely to get blocked by the firewall. Okay, so the basic idea of this is also very simple. Let's say first the server here, server address, this is actually the attacker's address. The attacker has an IP address, and let's say this is attacker's IP address. This is attacker's port number. Then on the exploit system, it will execute this piece of code. It will first create a socket. This will be a TCP socket. Then it will try to connect to the attacker's computer. After it connects to the attacker's computer, it will get a file descriptor for this collection. That file descriptor is in SOC, and this file descriptor, we are going to duplicate it to this program's std in, std out, and std error. So after that, we execute the shell. So this is the same thing. So the shell program still executes on the victim's computer. However, it is binded with a socket which is connected to the attacker. And in this case, the victim actively initiates the collection to the attacker. Any questions?
No, I'm good.
Okay. Cool. So next we will talk about how to make share code more injectable or disableable, aka share code encoding. We have been studying something related to this already. At the very beginning, we have our share code without zero, right? So this is our local long share code, which just print out the flag. So this piece of share code doesn't have any zeros. The reason we don't want it to have zeros is because some of the vulnerabilities are like string copy, those kind of vulnerabilities. They will stop when at the end of a string, and zero indicates the end of a string, right? So because of that, we cannot have a zero in our share code. And we actually replace some instructions to equivalent ones, so we do not get zero. For example, here, we're using exclusive OR EAX, EAX. The idea of this is to make the content in EAX zero. Obviously, another more straightforward way or easier way to write this is just to move EAX zero, right? Directly move the value zero to EAX. However, there are several disadvantages of that approach. First, that zero immediate number itself is 4 bytes. So the instruction will be longer than 4 bytes. However, the exclusive OR EAX instruction will only be 2 bytes. More seriously for us is that we'll have 4 bytes of zeros in our share code to represent the value of zero. and it will make our share code not usable in many cases. We have also seen other cases, like we are taking input from the command line arguments, right? When we take input from there, when we put share code there, we in some of our programs, we first check how many arguments, command line argument are there. And there are other ASCII values can break the string into multiple strings, like what you discovered there, like 20, and there are others as well, right? 9C or 9F, a vertical 10. So those will make the share code read like two pieces of independent strings. So make the share code not usable. That's why sometimes we need to change our instructions so the instructions will not have those sensitive bytes, right, to make our share code more injectable. Instead of making the code more injectable, sometimes we also want to make the code more disableable. So if you are looking at this piece of share code, you do not even realize this is share code. In 2009, there was a paper called English share code. So what was proposed in this paper was approach to turn into existing share code, like the ones where we have been using, into readable English. But they are still code, but somehow they're readable English. For example, here, this is a piece of share code. The share code read like decent English, readable English, right? Not necessarily good one. For example, there is a major center of economic activity, such as Star Trek, including the Ed Sullivan Show. So all of this, they are readable English, maybe not very good ones, but every letter here, they are also just an ASCII value. And that ASCII value could represent a different opcode as well, right? So in this case, there is a major, those 12, 15 letters, they represent 12, 15 bytes. And that 12 to 15 bytes can be interpreted as those 5 instructions, like push ESP, push this particular value, multiply those values, another push and another jump, right? Then in the middle, we can have some fittings, kind of like no knobs, no operations to make it read like more like English, but they are not really valid instructions. But we're not going to execute them either because there is a jump. Yeah. So in this piece of code, in this piece of English paragraph, code part is the black part 1, 2, 3, 4, 5. Other parts, they are kind of like knob operations, or they are not even knob operations. They are just the filling scheme. So this is what proposed like 15 years ago, English share code, right? Amazing. So when you are chatting with someone online using WhatsApp or other instant messengers, the people who are chatting with you may be sending you share code. They may be trying to exploit your system, and they read like English, right? Then in 2017, there was another interesting paper presented at Usenix Security about DNA share code. And the idea of this is also very, very, I would say, interesting and also stunning. So in this case, we have a DNA synthesizer. It's a machine, or a DNA sequencer. It's a big machine. And that machine has some physical parts, has some cyber parts, has computers, has CPU, has software. And as long as it has software, it may have vulnerabilities, right? It have the vulnerability of buffer overflow, the ones we have learned. let's assume this DNA sequencing machine has a DNA sequencing software which has a buffer overflow. But the input to that software will only be valid DNA sequence, which means can only be CTAT or G, right? CTAG can only be those 4 letters, nothing else. So how can we encode a very complicated shellcode like what we saw before, right? Like 20 bytes, 40 bytes, 120 bytes. But now we can only use 4 letters, CATG, to encode that. Previously, in our local shellcode, the only limitation we have is we cannot use the zeros. We cannot use zeros. Everything else we can use. Then in the whole 256 possible values, only 0 we cannot use. Then if we use that in command line, we say there are several others we cannot use, but we still can use maybe 250 values out of 256 possible values. Now we can only have 4 values to use. How can we encode that? So they prove that this is actually possible. They can write a shellcode, use only those 4 letters. Yeah, which is amazing. So then they actually synthesized those DNA samples. So it's physically a DNA sample in a tube like this. They put this tube, the content of this tube, the DNA strings, into this physical machine. And this physical machine will get the DNA sequence, which will be something like this, and feed this sequence into the software. And the software has a buffer overflow, and it will be exploited by this. So this is a very stunning cyber physical attack. Clearly, the cyber parts, there are physical parts, yeah, which is amazing. So in this class, actually, I will ask you guys to develop some shellcode, but your job will be much easier. We're not going to do something super crazy. We will use our existing shellcode, and you need to change existing shellcode to bypass some of our sanitizers. So next, I will explain how our sanitizer works and what is the template for you to develop the shellcode. So you can use online tools, which will be much easier, or you can also compile this on our server on your local machine. If you want to compile your shellcode on your server or your local machine, then you can use a template like this. And you are going to use Intel syntax here. You just write your instruction here by here. Then at the beginning, you write something like this, only 3 lines of template. Then after that, you can use those commands to compile those shellcode. To compile that, you use GCC. If it's 32-bit, you use GCC -M32, which means this is a 32-bit program. Dash no std lib means we don't need the standard library. Then this will be statically compiled, and your shellcode will be this one. The output will be an L file. But obviously, L file is not the shellcode you need. What you need is just the raw bytes. We already talked about this in the first class. The L file is very complicated. It has many headers. It has many sections. It has a lot of metadata, which we don't really need. What we really need is just the instructions. We need the raw bytes of the instructions. That's why there is another tool called OBJ copy. And we use this tool to dump the code section of the shellcode the L file generated. Then we can get the raw byte of the shellcode. The 64-bit version of this is similar. Okay. So if you feel this is too complicated, actually, it's much easier to just use some online tools. So I give you guys a link here. This is an online tool. You just write your instructions. It will directly give you the corresponding bytes. So your shellcode will go through some sanitizers, or we call it testers. All the testers, they will look something like this. The tester is a C program. You will feed your program, you will feed your shellcode into this program. And this program is very simple. It doesn't really have bugs. It will just execute whatever you give them. But after doing some sanitizing, for example, you will first create. Sorry, let me close my door here. Sorry about that. So this program will first create one memory page. That will be 4K. That's quite enough for us. We're not going to write 4K bytes of shellcode. Then after that, it will read from std_in to that memory location, then just execute from there. That's it. So that's a tester. So this tester, obviously, no matter what you give to it, it will execute. Then we will have two more testers for you to work on. One is a non-zero tester. You need to develop shellcode that doesn't have zeros, because instead of doing a memory read of everything like before, this one will read it to a buffer first, then use string copy to copy from the buffer to the memory page to execute. Because it uses string copy, your shellcode cannot have zeros, right? Another one more interesting is this one. You will only be allowed to use ASCII characters and the printable ASCII characters, which means from 0 to 128. So you are using just half of you can just use half of the possible value.
Is the map overriding memory or something?
So no, the M map here is not overwriting any memory. It creates a new memory page. So there is no overflow or any vulnerability here.
So where the page is saved? Like if you are not overriding the memory, then there's some place to save the code that you are writing, right?
Yes, but in this case, so for all the programs, it has a 4 GB virtual memory address. We talked about that before, right? For 32-bit version.
Right.
So that 4 GB virtual address are not fully mapped. So some of the address, they do not have anything there. It's not physically mapped. There is no physical memory to back it up, basically. That's why if you access those memory addresses, you will get a segmentation fault because nothing is there. You will get a denied access, a page fault, something like that. Does that make sense?
Oh, right. Yes.
So the memory map is create a new page for you that doesn't exist before. Now make a new page available for you, available for this program. Then this piece of code will put your shellcode at that page. So it will not overwrite any existing memory locations. Make sense?
Yes, yes.
Okay. So then this piece of code, you can say it will do a ASCII copy. It will only copy ASCII, printable ASCII numbers. And to make things a little bit easier, I do allow you to use CD and AT, so you can make system calls. Because you are going to make several system calls. Without this, is still possible. Basically, you need to reconstruct the CD and AT in memory. That will be much harder. Yeah, so I make it a little bit easier. So that's basically what I want you guys to do in the next class after after the midterm exam. So I will be there to guide you guys. So that's basically it for today's class. Because all the details, we can talk about them when we develop the share code together. Do you have other questions?
No, not for this class.
Okay, cool. So this one will not be in the midterm. What we discussed this Tuesday will not be covered in midterm either. So I will soon release some guidelines for midterm, including the rules and what kind of, well, I already told you the rules, but there will be more details about what will be covered there. Cool.
Okay, okay.
So
Thank you so
really,
much.
Thank you very much for showing up. Okay, I guess that's it. See you in 2 weeks.
Okay, see you soon.